Welcome to the first episode in a series where I'm providing updated information for my DIY PCB tutorial. Yep, I've been doing some of that coding for the hi-hat pedal as I discussed in the earlier introduction video. Honestly, I'm struggling a little bit to get in the zone, but it's always a bit like that. So making this video is going to give me a bit of a break from all that, I guess. Now, I struggled a bit with what to show in each of these episodes or in what order to release them, but in the end I've decided to mostly follow the order that I used in the original tutorial video. Some of the episodes will likely be less groundbreaking than others, but they all contain useful information. So in this video I'll be talking about the equipment that I really think you need to replicate what I'm doing in that tutorial video, and also will be included some discussion on how to achieve the best possible accuracy. Anyway, let's get straight into it. So here's my basic equipment layout for when I'm making my PCBs, consisting of my CNC 3018, control PC, air compressor for air assist, ventilation, hot plate, a UV light box, electronic microscope, watch repair glasses, and a few other bits and pieces that I need for applying the UV resin. Anyway, what I love about this setup is that it's really super compact, and I'm usually just standing or sitting around the same spot to complete the entire process. So first let's talk a little bit about the CNC, as it really is the star of this event. As you probably know if you saw my earlier videos, this is actually a rebuild of the cheapest bare-bone CNC 3018. And honestly, I think I've rebuilt it in a way that far exceeds what you really need just to make PCBs. That's really as a result of me not really knowing what was actually causing all the inaccuracies that I was seeing. So basically any upgrade that I could do at a reasonable price, I did it. Obviously I got a bit of a bonus out of that because now the CNC is much better at machining metal, so I'm not really complaining about it at all. And there's always plenty of opinions in the comments about how you probably should have done this or you should do that. But let me share my current view on what I think is really important, based on my experience to date. Firstly, of course, more rigidity is always better. But if you only had a cheap 3018 like I started out with, then a small modification like adding some of these 90-degree corner brackets here and there would probably be enough to give adequate rigidity. I mean, you have to keep in mind that the bulk of the work that is being done in this process is actually being done by the laser, and the drilling that is done is actually pretty super lightweight. Now, there are also a number of reasonably priced aluminium frame 3018s out there being sold now, and if it was me, I probably would be considering buying one of those. For sure, probably not going to provide the same level of rigidity as my rebuilt 3018 does, but overall it would be a market improvement compared to what that cheaper black composite frame gives. For the spindle, believe it or not, the rather pathetic standard brush motor that comes with that cheap CNC 3018 is likely going to be good enough for making PCBs if you're using my process. Even so, there are a number of aluminium framed CNC 3018s being sold that actually come with 500 watt brushless spindles. So if it was me, then I'd probably go with that. It also seems that many of those aluminium frame 3018s come with 32-bit controllers now instead of the standard 8-bit one. So that's another pretty big plus that should steer you away from the cheaper option. But of course, make sure it actually is a 32-bit controller before you actually go ahead and place your order. There's also a couple of different frame dimensions out there for these desktop CNCs. For example, 3020, which I think would be fine. And recently a viewer left me a comment saying they had purchased a 1419 with a solid aluminium frame. And that looks like a pretty nice compact option, so if you're limited on space, I guess you could go with that. For me though, I really do like my customized 3018. It provides a nice amount of workspace in all axes now, and for PCB work, there's really no situation where I ever feel compromised or inconvenienced by it. Now for the 450 nanometer laser that you're going to need for doing this process, I would recommend something that has an optical power between 5 and 10 watts. It should also have a fixed focus and include a nozzle for air assist. Now you might be tempted to buy something with even more power, but I suspect you might have trouble dialing in the power level for exposing the silk screen, so it's not something that I can recommend. Actually, recently I've had a viewer reach out to me about what laser to get. Unfortunately, the gold 40 watt laser tree unit that I currently use is no longer being sold, so I can't recommend that anymore. In any case, I highly recommend getting one that actually has a air assist nozzle included, and that one didn't have one, so it's not really a good option anyway. Interesting, however, they still do have a variable focus version of this old laser still being sold. It's probably old stock. They now sell it as having 5 watt of optical power for this supposedly 40 watt branded laser. So I guess that actually means the one that I'm using only has 5 watts. Originally I had read in the rumor brigade on blogs and otherwise that it only had around about 10 watts of optical power. But anyway, I guess it is what it is. So Laser Tree currently has two good options that I can see, one being a 5 watt version and the other one being a 10 watt version. The 10 watt version actually is being sold as having a symmetrical burn spot shape, which in theory could be a huge plus. I would also expect that the extra power could possibly make cutting out the PCBs a bit faster, but really other than that, it's not going to give you many benefits. Personally, I'd probably try to get the 10 watt one if I was going to go out and buy one now. It's actually pretty expensive at twice the price of the 5-watt one. So if you're on a budget, the 5-watt one is still a great option. Now, I think it's important to note that I have not used either of these two new lasers, so I cannot specifically vouch for them, nor do I have any affiliation with Laser Tree or AliExpress or anything like that. It's just a brand of laser that I have, and it seems to work okay. There are actually plenty of options out there for diode lasers if you go and do a bit of research, but generally I would recommend sticking to a major brand if you can, and do your research, make sure you check other people's reviews and see what sort of results they're getting. Now, for the viewer that I was chatting to about this, he was looking at purchasing a 3018 from a manufacturer called Lunyi, and this was bundled with a brusher spindle, and optionally you could add a 5-watt or a 10-watt laser. So going with the CNC that is bundled with a laser does actually seem attractive, since you can be confident that at least the laser is going to work with the CNC straight out of the box. But some of these bundles likely also include lasers which are not so great, so again, do your research before you go ahead and buy one. Now, with regard to actually getting good accuracy from a 3018, here are some of the changes that I made that I think made the biggest impact on my results. And first, let me sort out the terminology I will use the linear bearings that these CNCs use. There are basically two types, the linear rod bearings and the linear rail bearings. For brevity, I'm just going to refer to them as rods and rails in this video. Now, the lion's share of the 3018s out there being sold uses rods for all axes. Most of the time these are 10mm, but sometimes you'll find them with 12mm on a couple of the axes. Actually, I think the original cheap 3018 even uses 8mm ones on the Z-axis. So when I rebuilt my CNC, I upgraded to 12mm rods on the Y-axis, kept 10mm rods that came on the Z-axis upgrade kit that I had installed some time before, and I also changed my X-axis to use a pair of 15mm rails. The biggest improvement I got was clearly swapping the X-axis to using rails. I mean, it was like night and day. Before, when accelerating horizontally, my laser burn path would have a squiggly line shape, but this completely disappeared. I also saw dramatic improvements in positional accuracy in the Y-axis. Whereas before I was seeing shifts of close to 0.1mm, basically now I don't see any discernible shifting. Actually, back when I released the original CNC rebuild video series, I did have a viewer reach out to me and tell me that in his experience, the rods had too much play, and that I should have probably just gone for rails throughout, and not just the X-axis. At the time I told him the rods I had seemed okay, but actually I was completely wrong, and he was completely right. This was especially a big problem on the Z-axis, where there was still a huge amount of play. And during drilling operations, this would actually cause the whole Z-axis to rotate a bit, which, as you would expect, kills the accuracy, but it would even go far as snapping drill bits on the occasion, which is really not so nice. Anyway, I finally went ahead and replaced the Z-axis rods with a pair of 12mm rails, and that has made a world of difference, with basically no notable play now. Thankfully for the Y-axis, however, the situation was not as critical. This is because the orientation means that the weight of the bed is consistently applying pressure on those bearings. And that, combined with having bearings in all four corners of the bed, means that normally the play will not actually manifest itself. I actually think the only time that play might actually become a factor here is on aggressive drilling or milling operations. In some cases it could happen that the pull-out force of the bit from the work might just be enough to get the board to float a little bit, and in this case it might be conceivable that play becomes a factor. Anyway, it was a huge relief not to have to do anything, because I'd actually gone to a decent bit of effort and expense to upgrade to those 12mm rods. And to have to actually go ahead and upgrade the rails on the Y-axis now, that even looks more difficult and more costly. Even so, knowing what I know now, if I had not already switched to the larger rods, I may very well have gone with rails on the Y-axis as well. In the end, it would have just come down to budget, I think. So in summary, my recommendations are as follows. You will need 15mm rails on the X-axis. This is a bare minimum. And I also highly recommend using 12mm rails on the Z-axis, especially if you want good drilling accuracy. Rods on the Y-axis is probably fine. Of course, 12mm rods are going to be better than 10mm ones. But if you are considering upgrading, then of course using 15mm rails is definitely worth considering. But there's some good news here as well, because a number of those 3018s out there being sold right now already come with 15mm rails on the X-axis and 12mm rods on the Y-axis. So that's definitely very convenient. Though I can't say conclusively that this is going to be a cheaper option than just doing the upgrade yourself. But of course it's going to be a lot less hassle. Now, I couldn't find any 3018s out there being sold with rails on the Z-axis standard, so this is something you're probably going to have to need to modify yourself. In the case of my 3018, I'd already installed that upgraded Z-axis assembly on there some years before, so for me, actually adapting that to rails was pretty easy. And in total, I think it cost me around about $15 for the pair of 12mm rails, and that was really basically all the cost. So depending on what Z-axis assembly you already have, the difficulty level and the cost is surely going to vary quite a lot. Anyway, there are plenty of ways to solve this problem. You just need to find something that makes sense for your situation. And now for the controversial bit, the lead screws. Now, I did get comments saying that I should switch to ball screws, but actually I'd already considered it. And ultimately, I decided just to stick with the basic lead screw hardware. My budget for this project was already blown way out at this point. I was only budgeting around about $100 for the entire rebuild project, so purchasing somewhat expensive ball screws for all axes was just not an option. It also looked pretty difficult to figure out how to install those bulky ball screw assemblies into the original 38-inch frame. I'm sure it's not impossible, but it was just another factor that made me decide against it. Still, I was actually a little apprehensive about keeping those standard lead screws if I'm at all honest. That's because I was worried that these might actually be the root cause for the weird burn path artifacts and positional inaccuracies and inconsistencies that I'd been seeing. But to my very pleasant surprise, all of these problems disappeared after the rebuild. So while the lead screws may have been contributing to the problems due to their inherent characteristics, they were not the root cause after all. And honestly, thank God for that. Now, it's very likely that the cheap lead screws do actually have some minor inaccuracies that cause dimensional errors, but they're not clearly enough to be noticeable at the scale that I'm working at. And since you always relocate the PCB in the exact same workspace while you are actually making it, it can actually cause errors due to positional shifting or variations. It's probably also likely that the cheap lead screw hardware might wear out a bit faster than the ball screws would, but this stuff is super cheap, so if I need to replace them every couple of years or so, then I'm okay with that. As for the PC to control your CNC, it could be a normal box PC or a notebook PC, or as in my case, I'm using a silent media PC that I had kicking around. The spec could just about be anything in theory, but I would recommend having at least 8GB of memory, preferably 16, and one that uses at least a mid-low tier CPU from Intel or AMD, such as Ryzen 5 or Core i5. Definitely stay away from those N-series or Addendum style weaker CPUs. I know you can get them for around about $100 for a complete PC, but it's just not worth going there. Now for air assist, in the original tutorial video I sort of indicated that maybe it was only a nice to have and only used for cooling during the pad clearing operations. But since then my opinion has changed a bit. I now believe you should definitely get an air assist solution if you possibly can. It's highly recommended, and basically I use it now for every single laser operation. And the reason actually isn't for cooling, as it is in the case when I'm clearing the pads, but it's because moving the smoke out of the way quickly helps ensure that the full power of the laser is consistently reaching the work. It also helps to ensure that the laser lens remains clean, ensuring long-term power consistency. And if to prove the point, I've even found that by using air assist during the PCB cutout operation, I can now easily snap out the PCB with just the tips of my fingers, whereas before I was actually using pliers and a decent amount of force to snap the PCB out. In my case, I'm using a pretty expensive $1,000 compressor, which I originally was using for construction, but this is total overkill for an air assist solution. But there are plenty of air assist pumps out there on the market now for, I think you get one well under $80. Actually, there seems to be a dramatic increase in the makes and models that are available, which is pretty indicative of how mainstream air assist has now become. Sadly, I don't have any experience with any others off-the-shelf pumps, so I can't recommend a specific device, but I would generally recommend you get the most powerful one you can afford, and of course, again, carefully check the various reviews before you make the purchase. Ventilation, of course, is a total must. You need to ensure you capture the fumes while burning with a laser and make sure you pump them outside. For me, I'm just using this home ventilation fan mounted in a box and a flexible aluminium duct, and I wedge it under the bottom of the garage door to make sure I get the fumes outside. I simply cover the whole CNC38 with a cardboard box with some filter material covering the holes to let some air in, and some holes on the other side aligned with the fan box to get the fumes out. Honestly, this is a pretty inexpensive solution. It's really easy to use, and I don't actually have any intentions to change it. And honestly, there's no reason why you couldn't just use a couple of PC fans or something like that, as long as it does the job. Now, the PCB hotplate that I made in an earlier episode actually seems like a bit of a joke when you look at it, but it's turned out to be extremely useful. I use it for all sorts of things like heating etchant, curing the UV resin, soldering the PCBs, and of course it's a godsend when scavenging parts from surface mount PCBs or generally doing surface mount PCB reworking. Honestly, I don't think it really matters what type of PCB hotplate you might get, as long as it does the job again. And here too, I don't have a specific recommendation. I can, however, recommend the setup that I built. I think the iron was about $10 and the controller $10 or $15, and maybe another $3 for other bits and pieces, so it was super cheap. Honestly, I don't really use these cooling fans very often, so you don't really need to add those. And if there's actually anything negative I would say about this thing that I built, is that it's probably a little bit slow to heat and cool, and the maximum temperature is about 180 degrees. But that's still hot enough for what I've been working on. The UV box I used to cure the UV resin is also something that I made in an earlier episode. Seems like we've got a bit of a theme going here. It's actually built on a 50 watt LED UV lamp panel that was sold on AliExpress. I think I got mine for around about $10, and it seems nowadays you can pick them up for just a couple of bucks, so it's a total bargain. But as you might expect for the price, the build quality isn't great, but even so, it's been proving to work well so far, so I think it's okay. Of course, exposure to UV light isn't really good for your eyes or skin, so if you do buy one of these light panels, then make sure you build some sort of enclosure for it. Anyway, I'm really happy with the design of my UV box. It works really well. Pick it up, place it over the work, press a button, and that's it. Really simple. Funnily enough, one of my viewers called Tanky Turk reached out to me, and he told me that he actually made a clone of the UV box that I made. He even featured it in a video that he made about applying UV resin with a roller. Anyway, I will discuss a little more about his resin application method in a future video. For now, I've added a link to his video in the description, so make sure you check that out. Now, I was actually expecting there was going to be a lot of similar form factor UV light boxes out there on AliExpress, and I did a quick search, and yeah, I couldn't really find anything that sort of was similar to that, so that's a bit of a problem. So anyway, I guess it's going to be up to you to figure out what sort of solution you're going to find. Worst case, you can use the light panel like I've suggested. Another thing that I said was somewhat optional in my original tutorial video was the electronic microscope. But after a recent round of PCB making and doing some work in that regards, my opinion has changed a little bit. Honestly, I found it extremely useful, and I basically use it all the time. So here too, this is something that I think you should really seriously consider getting. Now, I bought mine a couple of years ago for around about $50, I think. Long before I even knew what I might use it for. I think it was on sale and it attracted me to it, the AliExpress sale. Anyway, there are some things that are a bit crap about it, especially the firmware in general, and the fact that it doesn't maintain the correct image ratio for save files. But none of that's a real big showstopper, I guess. And the large screen and the generally good image quality makes up for most of that. It actually seems that this model that I got is no longer available, but there does appear to be some new versions of it out there. So I assume it's going to be much the same, and with any luck it might even have some improvements. Actually, after doing a search, I found there is a huge number of makes and models of these microscopes being sold now. Many of them even less than $30. So that makes it really hard to know what might be good or bad. Generally, I would recommend getting one with a high resolution 7-inch screen, and of course one that gives a high level of magnification and good camera resolution and quality. The one I have also has a built-in battery, which can be pretty convenient, but generally you could probably consider that as a nice to have. And of course, here again, it's critical to check the reviews that people leave. Often people will leave images that will give you a good idea about what sort of image quality and magnification you might expect from the device. And of course, as I showed in the original tutorial video, you'll need a set of these watch repair glasses, regardless of whether you buy the electronic microscope or not. So make sure you get a set of those. Actually, they can just cost as low as a couple of bucks, but they are absolutely essential for the alignment process. Now, I'm not going to go over all the small stuff needed to apply the UV resin in this specific episode. I actually have some interesting changes related to this process, so that's going to get its own dedicated episode, so stay tuned for that. So for the remainder of the episode here, we're going to switch topic a little bit, and I wanted to provide some advice on how to achieve the best possible precision and accuracy based on my experience to date. As I've shared in an earlier community post, I've actually machined myself a new height probe, which is spring-based instead of the solid chunk of steel I was using before. This is because during the probing, you can actually visually observe the CNC continue to travel for a little bit just after it contacts the probe. Actually, this was the case for the homing sequence too, and the reason why I use springs for my precision end stops. I think you're going to find that most commercially available probing solutions out there include some sort of give, so the fact that I was using a solid chunk of steel before was pretty stupid in hindsight. And I also suspect it was the cause of accelerating the blunting of my drill bits. I've even changed the probing sequence a little bit. It now multi-taps at reducing feed speeds in order to detect the final position. This for sure improved the accuracy a bit, but even so, consistency is really not that good. And this is something that's always dogged me with the GRBL probing sequence. Ultimately, be it with my optical probe system that I made, or the homing sensors, or the general height probing, no matter what I do, the best consistency I can achieve is within plus or minus 0.05 millimeters, which honestly is pretty terrible. I don't actually even believe this is a hardware problem. Instead, I suspect this is a problem with the GRBL code itself, a problem with the way that it's implemented that causes this variation. Unfortunately, fixing a problem like that is too much work for me right now, so all we can do is be aware of the limitation and work around it. Honestly, the plus or minus 0.05mm variations for drilling PCBs or adjusting the laser focal height isn't a real showstopper, so I can just go with that. But for just about anything else where precision is an absolute must, it's just simply not good enough. The good news, however, is that my precision alignment methods that I demonstrate in the original tutorial video have proven to be extremely effective. I've used it many times now, and I always get excellent results. So I really do recommend people give that a try. But even so, there are a few minor tweaks that I've made to the alignment method, so let's talk about those. One small change that I made is that when aligning the spindle, instead of using a 1mm drill, I'm now using a 0.9mm drill. This is because I found it a bit easier to identify if the drill hole is actually center of the alignment marker or not. Another change is that for the alignment marker, I'm now using a larger piece of resin-coated PCB, which I just actually leave glued to the CNC bed across multiple different jobs. The pieces that I've been using recently is 32mm wide and 40mm high, and that's just enough to fit 6 different jobs worth of alignment markings, and I just keep moving 6mm to the right and burn a new pattern at the start of each job. And I actually found by doing this that it actually saves me quite a bit of time, so I definitely recommend it. And of course you can use whatever size piece you like within reason, as long as it's a multiple of 6mm wide and 40mm high. Another small change that I made is that once I get the alignment correct for either the laser or the spindle, I then go ahead and move the origin up by 4mm and do one extra test on the marker, just to make sure that the results are truly consistent. And if need be, then I might make some additional very minor adjustments. I find this is more important for the spindle, which has a little bit more mechanical randomness, but it doesn't hurt to do it with the laser as well. Now obviously this is not an essential new step, but for sure it can help to improve the precision. Now something a little bit more important that I've been doing to help improve the precision is to stop clamping down the work whenever possible. And instead, I just depend on the PCB guides itself to hold the work in place. Now after doing that, I've actually found a notable improvement in the alignment between the various operations. So clearly the way I was applying the clamping force was actually pushing the work slightly out of alignment. Now for the case of drilling where the drill bit could actually pull the work out of those guides, or for pad clearing where I'm using high pressure air and again you could end up getting the PCB blown out of the guides, you're still going to need to clamp down the work. But I'm taking a little bit more care with clamping down the work in these cases and using as light and as even as pressure as possible. Anyway, I think this makes a lot of sense and so far has been giving really good results, so I can definitely recommend you do the same. So enough for the recommendations and onto a little bit more discussion here. Actually, I've been finding recently that the operation to drill the holes into the PCB pads is actually pretty precise, but for some unknown reason, it's always just shifted a tiny little bit off center, and for some reason more often not to the left. I'm not sure why that is. But I currently do have a theory for why we are actually seeing a shift, and it goes something like this. As the drill enters the pre-etched opening for the hole in the pad, it just clips the copper at the edge of the opening, causing the drill to drag slightly off center. Now, I don't know if you know or not, but copper is a super sticky material to machine. It's so difficult to work with, so I think it's a reasonable theory. Now, possibly using higher RPM could make this less likely to occur, but I don't have more RPM available right now, so that's not a solution. So I think the better approach will be to stop pre-etching those holes in the pads. Now clearly all the alignment operations which drill just directly into the copper surface on the PCB have been pretty consistent and accurate, so I'm thinking that's probably going to solve the problem for the drilling of the holes in the pads too. Now of course what we're seeing here could just simply be the mechanical accuracy and consistency limits of the spindle itself, and if that's the case, well, I think it's probably good enough anyway. But anyway, we'll see how it goes. And finally, I wanted to point out that if you're only making single-sided PCBs with no markings or anything on the backside of the PCB, then it's always an option to just consider skipping the alignment steps you need for flipping the PCB. And of course that means you're going to be skipping the backside laser cut operations too, because you're not flipping the PCB. And that's going to obviously leave the problem of how you will complete the cutout of the PCB. I guess you could just manually complete the cut if you wanted to with some tools, or alternatively, dare I say it, you could always consider adding a milling operation to cut out the PCB. So in my mind, I'm thinking that by skipping the alignment steps needed for flipping the PCB might actually save some people some time, but to be honest, I'm not entirely sure either. Anyway, it's just something I thought I would share. For me, however, I always habitually do the PCB flip alignment steps, regardless if I'm doing anything complicated on the other side or not. And this is simply because I plan to do some double-sided PCBs in the near future, so I really want to hone my skills at the PCB flip alignment and really make it second nature. And if I'm really honest, I don't really like the idea of manually cutting the PCB or milling it out either. Anyway, I just wanted to say there are alternatives out there, so do whatever makes sense for you. Now, I actually did have one more important improvement with regard to accuracy, but it's something that I've decided that I will include with some other stuff that's coming up in a separate video. It specifically relates to the asymmetrical shape that you find with nearly all the diode laser that you get out there. It's taken me a little while to solve this problem. Well, it's taken me a few years actually, but I think I finally come up with a fairly easy and effective solution to address this problem. So that's it for this episode. Got any questions? Then whack them in the comments. Many more enthralling episodes coming up soon, so I hope to see you then.